Okay, welcome to lecture 5. Today will be an interesting lecture, a fun lecture, I hope, and something that will make everybody think a little bit. We're going to be talking about the asymptotic equipetition property, and in particular, we're going to, armed with the asymptotic equipetition property, we're going to come up with our first source code of the class. So this is today's sort of the real meat, or I shouldn't say that, it's meat, the real content of the class. So if you haven't already done so, read chapter 3. Actually, raise your hand if you have read chapter 3. Okay, everybody except for one person. You haven't read chapter 3?
Yeah, just a few lines.
Just a few lines? Okay. Has anyone read only a few characters of it? I read up until the word the, but then I stopped. Jokes? No. Okay, so homework 2. Now that you finished homework 1, homework 2 is due. It's due next Tuesday. Okay, so I hope everybody's doing okay with the homework. If you've got any questions or problems, please ask me. But basically, we're going to have a homework due, just to let you know, every Tuesday up until our midterm, which is going to be on Thursday, October 31st, I believe. I think that's our midterm. And I think that's announced the first day of class.
Can you post the answers to homework 1?
Sorry?
Can you post the answers to homework 1?
Can we post the answers to homework 1?
Okay, I'm still working on the basics.
Actually, I have the answers, by the way, if you don't have them. So I can give them to you if you don't have them. But yes, I'll give them to you and then you will post them. But yes, we need to post the answers as quickly as possible. Agreed. Okay, so, asymptotic equipetition property. So we said a little bit about this last time, so this is review. And we're going to emphasize intuition at first. And again, this is really important to read chapter 3. So raise your hand if you found chapter 3 a little bit confusing. Raise your hand if you didn't find it confusing at all. Raise your hand if you found it maybe slightly confusing. Okay, so hopefully by today we'll solidify. I'm very glad that actually most people read it. This is very good news. Okay, so let's just go through this really, really carefully, because I want everybody to understand this. I think it's really, really interesting and fun, and I hope that I will impart to you some of this feeling about this chapter. So we've got a block or a sequence of random variables. So all random variables, we're going to be talking about blocks or sequences of length n. Okay? And these are going to be our random variables, x1 through xn. They're going to be IID, and there's some distribution p that they're distributed according to. Okay? And there's p of x. So each IID random variables, that's a very simple set of random variables. And maybe they take a k-array alphabet, so we can talk about the alphabet being A1 through AK. Sometimes we'll talk about when k is equal to 2. So it's a binary alphabet. Sometimes we won't. And I'll try to make that clear. If you're ever at any point confused about what the source is and what we're compressing it down to or what we're setting it into, please let me know. Sometimes it's a little bit confusing because sometimes we're sort of taking a binary string and compressing it into other binary strings. Other times we're taking a non-binary string and compressing it into binary strings. So, but the point is that we're definitely compressing down things into binary strings. Okay? Although we might not start from that. And that depends on k. So when we look at a string of length n, there's k to the n possible strings, right? So we want to compress or encode. I mean, not even think about compress for the moment. Let's think about it just in terms of encoding. We want to come up with a representation for each of the k to the n possible strings, and we want to represent them with binary strings of length m. So we have m, capital M, possible code words. These are called the code words. So this is an important word, the phrase, the code words. These are, in some sense, the words that constitute our code, and our code consists of all of the code words. And we're taking strings and coming up with a representation of these original source strings in terms of our code word, and we're only sending or storing or doing stuff with code words, not with the original source. It's code, right? It's just, the word code basically means you're encoding something in a representation that's not necessarily the same as its origin. And that's called an encoder. So we've got k to the n possible strings here. source strings, alphabet size k. There's n source letters in each message. So each message consists of a sample of these n random variables. Did anyone see the light turn off when I waved my hand? Does that happen? Do I have magic powers? For our YouTube listeners, I waved my hand and the lights just suddenly turned off. And now I believe I have magic powers. But it's not working again, so I don't want to keep trying it because my belief in my magic powers will decrease. Okay, so now we encode it into strings of length m. Okay, and so of course it's a binary string, so basically every possible digit is 0 or 1. And so there's 2 of the m possible messages, and there's m total bits. We think of this as bits in our computer. And English letters is an example, so like k would be 26, ignoring punctuation and uppercase and lowercase. And then a source message, one of these source messages here, oops, I don't want to cross that out, I want to highlight it. A source message consists of these n messages. So here's a source message, which consists of n letters. Right? So every source message, and of course there's k to the n of them, should have a code word. In order for that to be the case, I mean, at the very, simple at least, we need to have m, which is true to the n. This is the number of code words, has to be greater than k to the n, which is the number of possible source messages. And so the condition then becomes m greater than log k of n. Or another condition, when we think about it in terms of the rate, and the rate, this is sometimes also a little bit confusing to people, but basically what we mean by bits, number of bits per source letter. So the units of the rate are bits per source letter, if that's not clear. Okay. So the rate is r, which is log m over n or m over n, lowercase m over n. So basically it's log k. So it's log k bits per source letter. This is our rate. And in general, this is sort of the quality of the code. This is our, not only an actual rate, but this is an average rate as well. Because if we do this trick where basically every message of length n, every source message of length n gets mapped to a bit sequence of length m, then if we take averages over lots and lots and lots of instances of this, we're going to have an overall rate, average rate of log k. So all source messages are going to be encoded with the same number of bits. And so rate is sort of a quality. This is a really important concept. This rate is going to be a quality that we're going to be using for source coding. Do we want high rate codes or low rate codes? High rate. So we want to use a lot of bits per source message. So does everybody agree with that? No, sorry, say again?
The other way.
The other way around. Which means what? Or somebody say it.
So more source messages per.
Right, so we want to have fewer bits per source message. So we want to have the fewest number of bits per source message, so we want to have a low rate code. Okay, if this isn't clear, think of this as data compression. Right? Think of it as English text. Each source letter is a character. Let's say it's 1 of 26. When we take a large collection of English text, do we want to use a large number of bits per English alphabet character or a slow number of bits? No, we want to use a small number of bits. So therefore we want a low rate code. Now that's how we're using the word rate, and that's how the book uses the word rate. And that's really important, and I think that's just that simple idea of like how the word rate and why it's a rate is important. So for English, we need, well, I should say naively, we need, under this scenario, log k, which is 5 bits per source letter. Yeah?
So, but this doesn't coincide with the definition for channel code rate.
We're going to use rate in a different way for channel coding. Right now we're talking about source coding. Okay. So when you're transmitting information, the rate, and I will fast forward a couple of lectures, what we mean by rate is the number of bits per channel use. Like every time we send one of these characters, or every time we send a message over a channel, how many bits can we reliably send over that channel? And that we want to be a high rate.
No, I mean the coding rate, channel code.
Right, so a channel rate we want to be high. I understand the question. So the channel rate we want to be large. A source code rate we want to be small.
How about the channel code?
Well, the channel code is the code which consists of the code words that we send over the message. So the code is essentially a mechanism for sending messages over a channel, over a noisy channel. But when we're talking about the word rate in the context of channel coding, we want a large rate. When we're talking about rate in the context of source coding, we want a small rate. That needs to be important. But we're not talking about channel coding yet. We haven't even introduced that idea. We're just talking about source coding. So in the context of source coding, we think of it as like you type out your homework in LaTeX, say, and you run gzip on it. And you look at the total number, total length of the LaTeX source, and then you count how many bits are in the gzipped file. So the rate is the total number of letters divided by the number of bits. Or I should say the number of bits divided by the number of, it's the opposite. It's the number of bits divided by the total number of letters. We want a small rate. And if the compression is good, the gzipped file is very small, and the rate is low, and we've done a good job in source coding. So what we want to do, like this is pretty naive, right? We're just basically saying that every source message has the same code word length, and can we do better and have essentially no error? This doesn't have any error, obviously, because there's a unique one-to-one mapping between source message and code word. And so the answer is yes, and we've already sort of seen this in the context of asking questions. The things that are very, very probable, the things that occur frequently, we don't want to use a lot of bits to encode. And the things that occur infrequently, it's okay if we use a lot of bits to encode. And the things that occur never, we can use as many bits as we want to encode, because if they never happen, it doesn't affect our overall rate. If something happens with probability 0, I could use as many bits as I want, any number of finite bits, and I don't change my rate, right? Because the probability of 0 means that won't happen. So here's one way of doing this. This is the first way we talked about it. So we have a bunch of source messages. So every dot here is a length end string. Maybe I should write that down. Every dot and I say source message or string, right? But I mean, it's the same thing. It's a string. We can talk about bit strings. We can talk about strings in our source alphabet. But the point is that every single dot represents a source message. And here, every dot represents a code word on the right-hand side. And basically, we have a mapping that basically different source messages map to bit strings. And it's a one-to-one mapping, right? So basically, this goes to this, and if once we encounter this code word, we can map that to the source message. So there's no collisions or anything. It's one-to-one. But basically, what we're going to do is, in order to get better than rate, is we're going to say that some of them maybe get thrown away. So that's kind of like what I said. Is that reasonable? That's one way we can do it, and we're going to find out that that's actually perfectly acceptable. That some of the source messages we just never bother encoding. Now, how can that be? Will we get an error? Yes, but if for all intents and purposes, these ones that we throw away never happen, will we get an error? No. Maybe what we can do, and this is the trick, we're going to essentially bound the probability of that error. And we're going to show that that probability of error decreases to 0 exponentially fast as n, the size of the size of the source messages, increases. As long as something happens, as long as the rate isn't too small. And can anyone guess what that lower bound on the rate is?
Entropy.
It's the entropy of the source. That will be the entropy. The entropy will be the fundamental limit of source compression, so that we can compress, and we're going to see this many, many times, and I'm going to say this over and over again. The entropy is going to be that value of the rate below which we can't compress. In fact, below which we're going to get a certainty of error. But if we're slightly above the entropy, no matter how, we can get as close as we want to the entropy, and the error will be bounded above exponentially going to 0 with n. So entropy is sort of this magical phase transition like point in this rate curve. So let me just say what I just said. So you're going to see this many, many times. And then we've got the rate. This is going to be good for the rate. And this is going to be bad. Okay, in terms of the error. So another strategy is to do this. So let's say, okay, we don't have ever have an error. We don't want to have any, no matter how small the probability of error, I don't care if the probability is smaller than the probability of the universe ending in 2 minutes from now, which can be about as small as these probabilities get, but I don't care. I don't want. I'm not even willing to take that chance. You know. So then you can say, all right. Well, what I'm going to do is these source messages that ended up going in error in the previous case are just going to go to long code words. So these very, very improbable guys are going to go long code words. The probable guys are going to go to short code words, and there we're going to get essentially the same rate. That's not going to be any better. We're going to see the same thing, that the entropy is the lower bound. This is what I mean by less distressingly, if you're distressed about inferring an error, we can do this. And we're going to analyze both cases. So this last bullet I basically said. Any questions on any of this? Yep.
Why would we get an error here?
No, in this case we don't get an error. But in this case we still have this lower bound on the rate. If we're trying to compress less than the rate, if we're trying to compress less than the entropy, we've guaranteed an error, pretty much. As long as the rate, I mean, this is not going to help us or hurt us in terms of the rate. So in other words, this error case and this case here is going to have essentially the same properties, and there's no advantage or disadvantage of either of them. Why? Because, as we will see, these guys are never going to happen. Unless, of course, you're talking about probabilities on the order of how likely the universe is to end tomorrow. Okay. So first of all, what's the probability of a source word? So it's an IID source, so basically we can factorize the joint probability distribution in this way. This is just a factorization right here. And we have the Shannon-Hartley information. So remember, the information about an event is I of x. We talked about this, I think, the first or the second lecture. So it's negative log of the probability of that event. So if we were to look at the information of this joint event, the joint event being that all of these random variables equal these particular values, that's represented by this information, which is the log, negative log of the probability of the joint, but then since it's factorizes and everything, we can write it as a sum. And then since it's a sum of these information, so it's sort of the sum of the individual information events, information of these events. So independent events are additive in terms of the information function, the Shannon information. And the other thing to note, of course, is that if we remember that entropy is just the expected value of the information of this random variable. So that's something we saw. Now, the weak law of large numbers, we talked about different modes of convergence. I didn't really go over that, but I was hoping that people would review those slides by themselves. So we're primarily going to be talking about convergence and probability. It's one of those modes. So I'm going to assume that people know what that is. I didn't want to just, we didn't, like I said, those are the previous slides. And I think you know that from your you should know that from your stochastic processes course. Does anyone? And if you don't, then you should. So either you don't know it and you should, or you do know it and you shouldn't. No, that's not right. Either you don't know it or you should, or you do know it, and that's great. In any event, we've got the convergence of probability. The weak law of large numbers says that if we take S of n, which is the sum of the set of random variables, sum of the set of random variables, and divide by n, it converges to the mean in probability, which basically means that it's going to deviate by the probability of the mean, of this sort of average mean, deviating from the mu by epsilon is bounded above by 1 minus delta for any epsilon and delta. For any delta, for any epsilon, we can find a delta where this is true, if n is big enough. And there's these, it's just the standard limiting argument. So, and then where S is the sum of ID random variables with mean. Okay, so then this information is a random variable with mean entropy. Right? So that means that if we take this sum, as the block length gets bigger, as n goes to infinity, this converges in probability to the entropy. Right? Weak law of large numbers. So if n is big enough, and this is what I said, this is where it gets cool. I mean, it's going to be, it's funny because the algebra is really simple in what we're about to do, but the consequence is profound. Okay, so follow the algebra and see if we'll see that suddenly this really interesting statement pops up. So, okay, fine. So weak law of large numbers, no problem. We take the average of the information functions, and let's just be a little bit fluffy for a minute and say it's approximately equal to the entropy, right? When n gets big, we can make it as close as we want to the entropy. Right? So that implies the following. That's just using the definition that negative 1 over n of log of the sum of the log of the probabilities is roughly equal to the entropy when n is big enough. Right? Multiply both sides by n. That's an easy thing to do, right? Let's put back in the full joint probability distribution. So, I mean, it's independent, so we can either write it in this way, or we can write it this way, right? There's no difference. It factorizes. And now let's take 2 to both sides. And we get, well, I should say 2 to the negative of both sides. And we get that the probability of this event is approximately equal to 2 to the negative nh of x. P equation doesn't zoom in. I can't zoom into all parts of this, so let's just highlight it. So this is I think, a remarkable statement, right? Because it's basically saying this is just any arbitrary sample, right? When n gets big. We're not saying anything about that sample. We're just saying that x01 through xn is just some sample of length n of these IID random variables. And we're saying regardless of the sample, its probability is equal to 2 to the negative n h of x. And note that this probability has nothing to do with the sample. This is not mentioning the sample. This is only mentioning the entropy of the random variable. So let's say it's a binary. Let's say it's a biased coin. Okay, I sample once, and let's say it's heads, 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 tails, tails. That has this probability. Now let's say I sample it again, and it's all tails. That has this probability. And then I sample it again, and it's all heads. That has the same probability. When I sample it again, and no matter what happens, I get the same probability. Now you might think, well, that's impossible, right? I mean, if I give you a fair coin where it's probability 0.9 of heads and 0.1 being tails, I can easily show you a length 5 sequence of coins where 0.9 is more probable than all 0.1, where all heads is more probable than tails. Right? So how can this be? Doesn't this seem like a contradiction? Somebody's raising their head no. So why is it not a contradiction? Wenbu? Why is it not a contradiction?
I think those things has a very low possibilities, so it will never happen. So in general, those happens are with these probabilities.
That's right. So the things that don't happen, we don't care about. What we're going to say, essentially, is that this is the asymptotic case. This is when n gets big, number one. This is not when n is small. It's asymptotically. So n might have to be very big for this to happen. Maybe it doesn't have to be that big. Thirdly, the only samples we care about are the ones, as you just said, the ones that really happen. Maybe some of these other ones don't happen. Or if they do, they happen with astronomically small probability. So that's basically the idea. So let's repeat here's the equation again, actually. When n is large enough, all events have equal probability. I'm going to repeat this several times. So this is startling. The right-hand side probability, it does not depend. It does not depend on the specific instance. Does everybody see that? Raise your hand if this is not clear. Or raise your hand if this is clear. This is easier. It's easier to get people to say this is clear. Raise your hand if this is clear. Okay, just how about mechanically? Is it clear? So mechanically, do you see how this expression here, this has nothing to do with the sample. So the sample is like the sequence of heads or the sequence of, whether is it heads or tails? The sampling is a particular pattern of heads, 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 tails, 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 heads, heads. That's what basically this stuff is. This is the sample here. And we're saying that regardless of the sample, whatever the outcome, and this is just, remember, so we have, let me just write this down, we have that x of I is sampled from p of x for all of I. So we just take n samples of a random variable, we flip a coin, biased coin, n times, compute its probability, and if n is big enough, it's going to be equal to this expression. And it has nothing to do with the actual sample. So another way of saying this, and this is sort of getting into the language of the book that people have a lot of trouble with, all sequences have the same probability. And let's say pretty much. Let's highlight pretty much. Pretty much all sequences have the same probability. So this is informal language, but that's kind of what's happening. And that probability happens to be equal to 2 to the negative nh, where h is h of x. So those sequences, let me just read this because I carefully crafted this language. It's worth reading. Those sequences that have probability, meaning like any probability, which means pretty much all of them, are called the typical sequences. And they're going to be represented by this set A. So the sequences that have any probability, then you're going to see that they're not, it's not all, it's all of them that, and we're being a little bit, we should say all of them that occur. Because the ones that don't occur won't have that probability, but we don't care about them because they never occur. So let's say this again. This is sort of a third redundancy. It's triple redundancy. So here's our sequence of IID random variables. If n is large enough, then for any sample, x1 through xn, the probability of the sample is essentially independent of the sample. Probability of the sample is only based on the entropy of the underlying probability distribution. Now, since they're all identically sampled, since all of these samples have the same probability, which is 2 to the negative nh, it's like a uniform distribution over those samples that have that probability. Right? If I tell you every sample has probability 1 over n, every possible outcome, let me make this more clear. Every outcome has probability 1 over n, where n is some number. Maybe I shouldn't use n because I'm using n in the sequence. Let's say every probability has every probability of every outcome has probability 1 over L. Let's use L. How many outcomes are there? L. There has to be L because they all occur. It's uniform. So that means that how many outcomes are there? There's 2 to the nh. There's 2 to the nh such samples. And it could very well be that 2 to the nh is much smaller than k to the n. Remember, k is our alphabet, n is the number of source letters. And depending on h, this could be much, much smaller than this. Right? Which means that I don't need to encode this many outcomes. I only need to encode this many outcomes because these are the only things that happen. So this is really what we're going to be using. A sub epsilon of n. So the epsilon is going to become clear soon. And the n is going to just represent the the length, the number of source letters. So what this means is that a large portion of our domain essentially won't happen. So it could be that 2 to the nh, which is this, which is going to be the size of our typical set, is in fact quite a bit smaller than all the possible source letters that could occur. I mean, this could be significantly smaller. And in such case, this actually sounds really good.
Good question.
Yep.
Also, But that only, so basically a large number of the events never happen if the distribution is not uniform. Is that right?
Yes, but we're going to clarify that because we're going to talk very specifically about even the uniform case as well. So, if I told you that I flipped a fair coin, I'm moving ahead a couple of slides. I've got some slides on this particular point. But if I say I flip a fair coin, let's say I flip it 1,000 times. If I told you, yeah, about 500 times it was heads and 500 times it was tails, you'd be unsurprised, right? On the other hand, if I told you I flipped a coin 1,000 times and 998 times it was heads and 2 times it was tails, would you get suspicious that the coin was fair? So while the probability of that sequence of 998 heads and 2 tails is exactly the same as the probability of 500 heads and 500 tails, there's something about the imbalance that seems surprising and extraordinarily unlikely. And we're going to quantify precisely what that means.
So intuitively, the case where you only have 2 heads and 998 tails, that would be one of these very improbable events outside the typical set.
Well, we haven't defined the typical set yet, so let's formally define the typical set that's actually not going to be, we'll make that clear. And I'm not 100% sure even we can answer that question today because we might need to talk about the method of types, because that's a very interesting question which I want to get at. But let's first of all define the typical set and gain some intuition. But remind me of that question because that's important. Okay, so A is our notion. This is the typical set of typical sequences, and the typical sequences we're right now only informally defining as those with probability to the negative nh. So here's kind of what I said. So if all events have the same probability p, then there are 1 over p of them, right? And so the number of typical sequences should be about this. Should be 2 to the nh. So the probability is 2 to the negative nh. The number of them are 2 to the nh, right? And so thus, to represent a code for typical sequences, in order to code for typical sequences, we only need nh bits. So we can take m, the number of bits, to be nh. Right? So what becomes of our rate, n over m? What I want to do is this. I want to keep this here. This implies, so our rate becomes n of m over n, which becomes approximately entropy. So this is the intuition. So basically, suddenly the entropy seems to be what we can compress down to. And so remember, here's just the same figure we saw before, just for your reference. Now this rate could be potentially much smaller than log k, right? Before we said it was log k. So what was log k? Remember, k is the number of alphabet symbols. What we mean by the entropy, this is entropy of x. So what did we say about the entropy? We have the entropy bound, which is 0 less than or equal to h of x. And what's the upper bound on entropy? Log of k, right? So that's the upper bound on the entropy. And depending on the entropy of the distribution, if the entropy is small, we can encode at a rate, a small rate, much, much lower than log k, which is really good. In the worst of cases, when does the entropy equal log k? For the uniform distribution. And so it seems like the uniform distribution is the worst case. But that's also not surprising, right? The uniform distribution, as we said before, is sort of the least predictable. It's the most capricious of those distributions that we could consider, right? It's the one that's the most intractable. It's the least reliable. All those nice words we can use. to describe probability distributions and anthropomorphize them. So we don't like uniform distributions from this point of view of compression. But as we'll see when we get into channel capacity, we do like uniform distributions from the perspective of communication. Okay, so let's see where this goes. So entropy shows up as the probability of the typical sequence. The number of typical sequences, which is this. Oops. And lastly, the number of bits per source symbol used when we compress, when we do this, when we code only for the typical sets. Okay, so let's set up. Let's be a little bit more. Well, this is, I guess, still sort of emphasizing intuition. So today's gonna be, because, like I said, it's oftentimes difficult to get around this concept. This is sort of the first major hurdle of this class. Once you get over this roadblock, the rest of the class is basically applying this same concept over and over and over again. So this is sort of the fundamental barrier to break through into information theory, is the typical set theory. So once you break through this barrier, you're sort of home free in terms of conceptual stuff. I mean, everything else, you say, oh yeah, that's like the typical set thing. Oh yeah, that's right, that's like typical set thing. And pretty much the rest of the quarter we're going to be saying, oh yeah, that's kind of like typical set theory. It's not exactly the same. Of course, it's more evolved, but it's not really conceptually dramatically different. So we're going to spend a lot of time saying the same thing over again in this class. And in fact, I'm going to spend a lot of time saying how I'm going to be saying the same thing over again in this class, at least in today's class. So we've got a bunch of IID Bernoulli random variables, and winched in their probability. So we can actually sort of write the probability very concisely as p raised to the number of times that there was a 1 times 1 minus p raised to the number of times that there's a 0. Now there's 2 to the n possible sequences. This is a binary alphabet. So this is now where k is equal to 2, because we're talking about x, right? Do all these sequences have the same probability? Do all 2 to the n sequences have the same probability? Did I say p was 0.5? So do they all have the same probability? No. If p is greater than 0.5, what's the most probable sequence? All 1. And if p is less than 0.5, what's the most probable sequence? All 0. So therefore, they don't have the same probability necessarily. Okay. The most probable sequence, we've already done this. Okay. Okay. Now the funny question is, do all sequences that have any probability have the same probability? And it's a little bit of a funny way of answering the question, so I can crispize this by adding the word collectively. Do all sequences that collectively have any probability have the same probability? What do you think the answer to that is, based on what we just said?
This answer is in the previous slide.
Yes? So I want to ask you the same question. So what's the answer? Yes, the answer is yes. All sequences that have any probability have the same thing. But what we really want to quantify is what do we mean by any, right? And for small n, right? So for small n, then the answer is no, of course, right? But for large n, something funny happens, and yes becomes the more appropriate answer, right? Okay, so the book, by the way, and we're sort of going, when the book says h, they really mean h of x. H of the source. So if that's confusing when the book only uses h, they drop x all the time. But we really mean h is equal to h of x. It's the entropy of a single random source variable, right? Just the source. That's what entropy we're talking about. Now here's a funny question. It's the probability of x1 through xn equaling alpha. Is that a well-defined thing to ask for? So first of all, remember we said anything can be seen as a function of a set of random variables, right? So we can talk about the probability of x that's really equal to the probability that the random variable x is equal to x, right? But then if we talk about probability lowercase of capital X, that's this whole thing is a random variable, right? It's a random variable that happens to be a probability whose values lie between 0 and 1. So therefore, it's perfectly sensible to ask for what's the probability of this random variable, p of x, equaling some value. And that's all we're doing here, but it's a vector value case. So everybody happy with this? It's the probability of the probability. Because again, we're being very specific about the capital letters here. And I think I just said this. So p of capital guys is a random variable. Now, another way of saying essentially what we've been saying is that the probability of this set of random variables being approximately 2 to the negative nh is approximately 1. So essentially it means, does it mean that this is a constant random variable? That the x's are constant? No, x's are not constant. Does it mean that this guy is a constant random variable? The probability of the vector? But it means, if let's say that instead of saying approximate, let's say it's equals, it's essentially, it means that it can be thought of as being essentially a constant random variable. So, and what we're going to see is that as n gets big, it approaches a constant random variable. So even though, and this is what's weird about it, is because even though the argument for this function is not constant, when we ask for its probability, that probability becomes constant. So obviously we're using this exchangeability of, when it's IID, any permutation has the same probability. So in some sense, this is a distribution that's exchangeable. It's called exchangeability in statistics, or permuted, or it's also a form of symmetry. Think of it as a symmetric thing. It's symmetric of permutations. We're not going to prove this in this class, but stationary or ergodic stochastic processes also have equivalent forms of this. But right now it's sufficient to talk about IID sources. But in English then, and then again, this is getting back to the language that the book uses, almost all events that occur with any appreciable probability are all equally likely. Okay, so here's Bernoulli trials, and we construct a binomial, which is the sum of n Bernoulli variables. So it's binomial NP. Okay? And so its expected value, this is S sub n is the binomial random variable. The expected value of S of n is n times p, average number of heads. The variance is NPQ, where q is equal to 1 minus p. This is something that you've all seen before. And it has distribution as follows. Okay. So then we're saying, okay, 2 to the negative nh. We're saying that that's a probability. The question is, does that even make sense as a quantity? So let's just write this down. So 2 to the negative nh is equal to 2 to the negative n. And let's put in the entropy. So the entropy is negative p log p plus 1 minus p log 1 minus p. Okay. And let's just solve for this. So it's 2 to the log p to the np plus log of 1 minus p raised to the n1 minus p. And it's equal to, then the 2 and the log cancel out, so you get p to the np times q to the nq. So this quantity then becomes exactly analogous to this part. This part here, of course, is just binomial coefficient. It's n choose k. It's basically the number of sequences of length n that have k1s in them. Right? And so the probability of Sn is equal to k is basically it's the number of sequences that have k1s times the probability of a given sequence having k1s. And we're saying that each sequence has this probability to the negative nh, and that corresponds exactly to this part, the yellow part. So that seems to check out. Right? So 2 to the negative nh seems like a sensible probabilistic quantity. Okay. Everybody understand? So physics fixed number ones. Okay, so in other words, all sequences that occur are the ones where the number of ones and zeros are roughly equal to their expected values. Right? No other sequences seem to have any appreciable probability. All right, so we already said this. Okay, so that's sort of we need to sort of make this a little bit more formal. So first of all, let's just state the main asymptotic equipetition property theorem. It basically says that we're in this setting where we have n random variables. They're IID, all distributed according to p. Then basically if we take negative 1 over n over the log of the probability, that approaches in probability the entropy. And the proof is remarkably simple. We just look at this quantity. We write it using its IID assumption. We turn the log of the product into the sum of the logs. And then we use the weak law of large numbers to say that that converges in probability when n gets big to its expected value, which is equal to the entropy. So that's all we really need. That's all we needed in order to demonstrate. Now, in order to sort of make this very precise, we need to start talking about specific bounds on these quantities and define precisely what the typical set is. And so in order to do so, we need not only an n, but sort of in some sense a tolerance or an error, which is epsilon. I waved my hand again and the light turned on. So what we're saying is that the set of sequences, any sequence that has the property that its probability is upper bounded by this and lower bounded by this is going to be typical. So another way of writing it is that the typical set is equal to all sequences whose average probability is epsilon close to the entropy. These are 5.28 and 5.29 are identical. And any sequence whose probability, its negative 1 over n log probability, is not epsilon close to the entropy is not typical.
Good question. Why is there an upper bound on the probability? Because that seems to be saying the probability of elements in the typical set is upper bound. Oh, okay.
This is just a sandwich discussion. So
Okay.
basically, I have a picture that describes it. So this is the log probability of the typical set. So here's log of 2 to the nh, which is right here. And we're saying that any sequence whose log probability is within this range is called typical. So it's basically, it's got a parameter. It's epsilon typical for a given n. So epsilon is another parameter of our typical set. So we're being more precise here, and we need to talk about epsilon, which is sort of like a noise tolerance or a slack or something, whatever you want to call it. So we want to have an upper bound and a lower bound, right? Because it's in some sense symmetric, right, around this thing. We think n epsilon is the diameter of our range, or our log probability range. And we can write it in two ways, in 5.28 or 5.29. In 5.29, we're doing this with the absolute value. Okay. So let's now look at this typical set and be formal about it. And actually, maybe we should take a short break. I'll keep this definition up. You can look at it, but let's take a break, and I'll see you in a couple of minutes.